Find the length of the longest matching DNA string. In this problem, two strings of DNA are provided. The strings are composed of four different types of molecules called bases, where adenine and thymine form a matching base pair, and guanine and cytosine are also a matching base pair. So, for example, adenine in string A matches with thymine in string B, but adenine in string A will not match with adenine, guanine, or cytosine in string B. Similarly, thymine in string A can match with at most one adenine in string B, but cannot match with another thymine, guanine, or cytosine in string B. Since one base can match with at most one other base, the longest matching substring is at most the length of the shorter of the two individual strings. Since the length of both strings A and B are 7, the maximum length of a matching DNA string would be 7. However, if string A was only 2 bases long, then the longest matching DNA string would be at most 2. In fact, by observation, we know the longest matching DNA string for this example equals 2, because adenine in string A will match with the only thymine in string B, and the thymine in string A will match with either the second adenine in string B or the third adenine in string B, but it cannot match with the first adenine in string B because matching base pairs cannot crisscross. For this problem, LENAB represents the longest matching DNA string, also referred to as substring, between strings A and B. For our problem, string A will be m units long, and string B will be n units long, where both lengths equal 7. We'll loop through string A using variable I, and we'll loop through string B using variable j. With this notation, we can refer to each base by the string name and its position in the string. We can represent substrings such as the first two bases in string A equals A2, and we already computed length A2B7, which is 2. Since n equals 7, we can simply write length A2B equals 2. Our rule for determining the string length is as follows. For a string terminating in cells AI, BJ, the length will equal 0 if I equals 0 or j equals 0. If base AI matches BJ, then length AI, BJ will equal length A I minus 1, B j minus 1 plus 1. If AI and BJ do not match, length AI, BJ will equal the maximum matching substring between length AI, BJ minus 1 and length A I minus 1, BJ. When I equals m and j equals n, then length AI, BJ can be represented as simply length AB. This length function we just defined will be used as we loop through string A and string B. At this point, it would be easiest to set up a table where string A is listed across the top and string B is listed along the left side. Also, keep in mind our designations for each base AI and BJ. We'll begin the algorithm by assigning variable I equal to 1 and variable j equal to 1. Next, we'll determine the length of the longest matching string for A1, B1. Since adenine is not a matching base pair with adenine, then the longest matching string equals the maximum of length AI Bj-1 and length AI-1 Bj. After plugging in 1 for I and 1 for j, we're left to find the maximum between matching length A1 B0 and matching length A0 B1. Since either I or j equals 0, we know the longest matching substring equals 0 for both cases. So we'll input a 0 into our table. Next in the algorithm, we'll increment j to equal 2, which means we'll next evaluate the cell for I equals 1, j equals 2 in the table. For this cell, adenine, A1, does match with thymine, B2. Therefore, length A1, B2 equals the length of AI-1, Bj-1 plus 1. After plugging in 1 for I and 2 for j, we know the length of A0 B1 is 0, because the string A index is 0, and 0 plus 1 equals 1. After incrementing j by 1, we would normally move on to I equals 1, j equals 3. However, we don't need to evaluate this cell because we already determined that the matching substring is at most the shorter length of the two individual strings, which means length A1 B3 is at most 1. And since length A1 B2 equals 1, we know cell length A1 B3 is at least 1, which means length A1 B3 equals 1. For this same reason, all the remaining cells in column A1 equal 1. Next in the algorithm, we'll increment I to equal 2 and start column A2. Since thymine in A2 matches adenine in B1, then the length A2 B1 equals the length AI-1 Bj-1 plus 1. And after plugging in 2 for I and 1 for j, we add 0 to 1 and get a total matching length of 1. For cell A2 B2, since thymine does not match with thymine, the length is the maximum of length A2 B1 and length A1 B2, which equals the maximum of 1 and 1, which is 1. For I equals 2, j equals 3, thymine matches with adenine, which means length A2 B3 equals the length from A1 B2 plus 1, which is 2. Since the longest matching substring between two strings is at most the length of the shorter of the two individual strings, then for I equals 2, j equals 4 through j equals 7, the maximum length is 2. And since the length A2 B3 equals 2, the minimum length is 2, which means the remaining values in column I equals 2 equals 2. At this point, we've completed the first two columns in the table, columns A1 and A2. We'll complete the rest of the table using the same algorithm. And our final answer will be located in the bottom right corner of the table, which means the length of the longest matching DNA string between string A and string B is 5. When reviewing the possible solutions, the answer is C. If we want to figure out which 5 matches were made between strings A and B, we'll first identify all cells where base AI and base BJ form a base pair. Next, we'll start at the bottom right corner of the table and follow the following traceback procedure. If cell AI BJ is a matching pair, which it is, then draw an arrow up and left. If the value in the cell to the left is equal, which it is, draw an arrow left. If the value in the cell above is equal, which it is not, we would have drawn an arrow up. Else means if AI BJ is not a matching base pair, which does not apply for this cell. And lastly, follow all the arrows and repeat the traceback process until length AI BJ equals 0. If we next perform the traceback for the cell containing the 5, this cell is not a matching base pair, so we can skip the if clause and move down to the else clause, which instructs us to draw a left arrow or an up arrow to whichever cell has the greater value, which in this case would be to the left, since 5 is greater than 4. After completing the traceback for all the cells, we notice the optimal solution of length 5 is non-unique. The matching base pairs for the first optimal solution are A1B2, A2B3, A3B4, A4B6, and A5B7. The matching base pairs for the second optimal solution are A1B2, A2B3, A3B4, A4B6, and A7B7. And the matching base pairs for the third optimal solution are A1B2, A2B3, A3B4, A5B5, and A7B7. These three optimal solutions are also traced out, and connecting arrows again represent matching base pairs for the first, second, and third optimal solutions.